Hi, everyone. All right, let's talk about some related rates, and I want to just give you some background information. That's why you're having to look at my face right now, because otherwise it's just a lot of me talking. Um, so related rates are a really common application of calculus. This is a way that calculus is used in real life situations quite a bit. And so what we're going to be doing is looking at some situations that can typically be modeled with some sort of formula, some sort of geometric formula. And in that formula, we're going to look at not just the individual variables as they are like in the moment, but how are they changing, right? Because that's what calculus is all about, is how are things changing. So the idea here is we're going to have some situation, and we'll do one of these in just a minute. We're going to represent it with a formula. And then what we're going to do is we're going to differentiate that formula in terms of time. And that's going to give us like twice the number of variables to work with, which I realize sounds scary, but for every variable, you're going to have the variable itself and then the derivative in terms of time, meaning how is it changing over time, okay? That's going to involve some implicit differentiation. So if you remember, that's when we were working with the y's and we would do a derivative and we would say, all right, we're going to name that dy dx. We're going to do kind of the same thing here. So I've given you some tips here, but I actually don't think the tips are helpful until we've gone through one example. So I'm going to go through example one, which is a pretty easy example. It's just got two variables involved. We'll do that, and then we'll kind of circle back up here and talk through these bullets, and then we'll do one of the harder examples down below, okay? So taking a look here at example one, an ice cube is melting at a rate of 5 cubic centimeters per hour. At what rate is the edge of the cube changing when the cube has an edge length of 3 centimeters? So these are the types of questions we're going to be answering. Is here's a situation, here's a rate of change. How does that mean some other value is being affected? Okay. So I do recommend always starting with a picture. This one, the picture is just of a boring old ice cube. And we, of course, are assuming that our ice cube is a perfect cube shape, but and the only information I know right now is that the edge length of the cube is 3 centimeters. So I'm just going to say the edge length is 3 centimeters. Arguably, E might not be the best variable to use here, but we're using this to represent edge length, okay? We do have another number going on here. The ice cube is melting at a rate of 5 cubic centimeters per hour, and we're going to talk about how to name that in just a minute. But what that's talking about is the volume change, right? This is a change in volume, cubic centimeters. That's the volume of the ice cube, okay? So what we want to be thinking about is how do you do volume of a cube? Well, volume of a cube is just the edge length cubed. So this is the formula that I'm focusing on. And then what I want to do is convert this to a format where I'm looking at rates of change. So that's going to involve derivatives. And so what I'm really doing is I'm going to come in here and I'm going to take a derivative of everything in this formula in terms of time. Okay, so I'm doing a derivative in terms of time. When I do that to the v, when I take a derivative of v in terms of time, that's just going to turn into dv dt. Okay, and so what that's talking about is change in volume over time. Now, for this e cubed, I have to apply kind of the same reasoning that we did when we did implicit differentiation, because the derivative of e would be dE dt, but then according to the chain rule, and that's really what you're doing when you do implicit differentiation, we have to multiply that by the derivative of e cubed, like use your derivative rules. So that's going to be 3e squared. Okay, and what it is that we're trying to find here, the thing that we're trying to calculate is at what rate is the edge of the cube changing? That is dE dt. That's this thing, right? That's what we're trying to solve for, which means I should be able to fill numbers in here and here and then solve for this thing, okay? So we know our edge length. Our edge length is 3. So I know that this side of the equation is going to be dE dt times 3, and then my E value is 3 squared. But then we also want to talk about dV dt. That's this guy, right? This is how is volume changing over time. and volume is changing by 5 cubic centimeters per hour, we also need to think about if that should be a positive or negative value, okay? Because it's melting, this means that we're decreasing, right? We're shrinking, okay? So this right here is dV/dt. That's how your volume is changing, but we need to list it as a -5, okay? Because it's decreasing. It's a decreasing value. So when you're thinking about these rates of change, we are going to have to think about whether they're positive or negative. And so in place of that dV/dt, I'm just going to put a -5. Okay. This side here, this simplifies down to 27, okay? And so really what I'm doing here is dividing by 27, and honestly a fraction would be fine, but I think it'll be easier for us to talk about like what this number means if I could turn it into a decimal. So -5 divided by 27 gives me -0.185 if I go to 3 decimal places. And so what I find as an answer here is dE/dt is equal to -0.185. And then that's a rate of change, right? Oh, I'm sorry, I didn't realize you couldn't see that over there. That is a rate of change. So that is I'm sorry, not cubic. It's the length, how the length is changing. So that's centimeters per hour. Okay? So what that tells us is that at this precise moment, when this edge length is exactly 3 centimeters, it is decreasing at a rate of 0.185 centimeters per hour, okay? So that right there is the answer to our question. But that's how these guys are going to work. And they get pretty ugly looking just because the formulas get very like lengthy like this. But you always just have your regular variables and then your rates of change, which are all derivatives, okay? So if you look back up at the top, and then I promise I'll take my face away. If you look back up at the top at these tips that I've given you, this is how we're going to start every problem. Draw a picture, and this is a huge deal, okay? If you get confused about where all these letters are coming from, the picture is the best place to keep track of those things, okay? Write out relevant formulas. That's your geometry formula. That's this guy. And sometimes we have to use that formula as it is to find values of some missing variables. That didn't happen here, but you're going to see that down here when we get to example 2. So there's some things that we might have to figure out using this formula before we can even jump into this derivative formula. Then you're going to go through your formula and take a derivative of everything, left to right. It's typically in terms of time. I can't really think of an example that wouldn't involve time, but I guess I'm sure there's something out there where your derivative wouldn't be in terms of time. But usually that's what these are. And we're using implicit differentiation, which means every time we take a derivative, we're going to say d whatever, dt, whatever variable we're talking about, and then apply our derivative rule. By the way, I didn't mention that here, right? I just said, hey, derivative of v is dV/dt. That's because the derivative of just v by itself would be 1, okay? And so since it's 1, I don't really need anything here. It's just a single variable. But here with an e cubed, I had to do some derivatives. And then once you get to that point where you have this formula, you should be able to plug in everything except for the one thing that you're trying to find. And I do find it helpful to, even if you have it labeled on the picture, sometimes go up into the problem itself and label like what each thing is. Usually it's hard to do though without a visual picture there to kind of guide you, okay? Okay, so let me see if I can make myself go back to full screen here somewhere. There we go. And let's work through example 2. Okay, so we're going to start with a picture here. Like I said, we're always going to start with a picture. I'll try to move that down just a little bit more. Sorry, my camera's not cooperating there. There we go. Okay. Police cruiser is chasing a speeding car and approaching a right-angled intersection from the north. So I'm going to say that this right here is my intersection, okay? And the police cruiser is approaching from the north. So the police cruiser is coming down from right here. And I'm going to label this P, just so we remember this is the police cruiser. I am worried about too many letters in my problem, so I'm probably going to get rid of that P eventually. But this is my police cruiser. he's chasing after a car that turns right at this intersection. Well, I guess they'd be turning left. They're turning toward the east is the point. So the person driving turns this way, okay? And so that's the car that the police cruiser is trying to catch up with, okay? Reading through this problem, and I'm going to start throwing some numbers in just a minute, but I want you to notice that at some point they use radar to determine the distance between them. So before I even put numbers on my picture, the distance between the police cruiser and the car is here along this hypotenuse. Okay, so we're going to have kind of three variables in play here. We have a length here, we have a length here, and we have a length here. This thing is going to involve Pythagorean theorem, okay, because I have a right angle here. I can use Pythag to deal with all these lengths, okay? And so now I'm going to go ahead and get rid of my P and my C, because instead I want to take this picture and label it with Pythag, which would be A, B, and C. And I know the formula that I'm going to be using is A squared plus B squared equals C squared. Okay, and actually I'm going to need some space for my other formula, so I'm going to move that over some. But now we're going to read through the problem and try to get some numbers on here. And I want you to try to differentiate between which numbers are rates of change and which numbers are actual distances. Everything we're talking about here is a distance or the rate that a distance is changing. Okay, when the cruiser is 0.6 miles north of the intersection, so there's my first number, 0.6 miles north. That's A, right? Because this is the police cruiser north of the intersection. So A is equal to 0.6. Okay? The car is 0.8 miles to the, well, it's supposed to be to the east, but I don't want to go down there and circle it. But that's this guy, right? That's how far this car is away. So this is 0.8. And the police determined with radar that the distance is increasing at 20 miles per hour. So this number here, this is a rate of change. This is not a distance. This is a rate of change. And it's the rate that this number is increasing. Okay? So what I'm going to label that as is over here next to the C, I'm going to say C is changing. That's what dc dt means, at a rate of positive 20 miles per hour. Okay? Okay, the cruiser is moving at 60 miles an hour. That's another rate of change. But I want us to think about this. If the cruiser is moving in this direction at 60 miles an hour, this distance is shrinking, right? This number should be getting smaller. So my dA dt, my rate that A is changing, is it's shrinking by 60 miles per hour. And what I want to know is how fast is the car moving, which is how fast is this number changing? This is where the car is driving, right? So what I'm trying to figure out is dB dt equals what? Okay? So we've got almost everything we need here. Okay, we've got our A, B, and C, and we've got our dA, our dB, and our dC over dt. The one place I want to point out is we don't actually have a value here for C. Now, what I would caution you about is we are in this problem going to have to figure out what C is, and that's not a big deal. But sometimes you have variables in your problem that when you take the derivatives, you don't actually end up needing those variables. So sometimes I would take and that's probably what I'll do here too, I will take the derivative of this thing first just to see what does that other equation look like so I know what variables I need to plug in. And then if there's something I'm missing, I might have to come back to this formula and find it, okay? Because like, for example, in this problem up here that we did, I didn't actually know the volume of the cube, right? I didn't know that the volume of the cube was 3 cubed, but I didn't need it because when I went over to this pink formula, the letter V didn't show up anywhere. But if it had, I could find it, okay? And so that's kind of what my process usually looks like, is I'm going to take the derivative first. So I'm going to take this guy, and I'm going to say, all right, derivative of A squared, that's going to be dA dt times 2a plus derivative of b, so dB dt times 2b equals dC dt times 2c. Okay, and I know that the dB dt, this thing, is what I'm trying to solve for. So I should be able to plug numbers in everywhere else I see letters. And this would be where I'd kind of take inventory. Like, do I have all of those other numbers? And I might notice that, hey, I don't have a number for C. So then I have to backtrack and figure out what the heck C is. Okay? Which is not hard. Ignore everything in pink. Okay? If I take away everything in pink and I just have that blue triangle there, I can use Pythagorean theorem. I can use this formula to figure out what C is supposed to be. So I'm going to plug in 0.6 squared plus 0.8 squared equals C squared. This is 0.36 and this is 0.64. So altogether this makes a 1. And then I'm going to take a square root and I find that my length of C is 1. Okay? Now I'm ready to head back over to this thing that I have here in pink. Okay? And I'm going to fill in everything that I know. So dA dt is negative 60 times 2 times my A value of 0.6. Well, I hope I don't run out of space here. dB dt is my variable. And that's times 2 times my B value, which is 0.8. Okay. dC dt is 20, and then times 2, and then my C value is 1. Okay, I do want to point out here, because you're going to be using Pythagorean theorem a lot. This type of situation comes up quite often. Back here in this original formula in pink, see how all of them have a 2 in them? We could have made this easier on ourselves by dividing everything by 2 to begin with. I didn't want to throw that at you in the first problem, but we could get rid of all of our 2's right now just by saying, hey, I'm dividing everything by 2. But this is not so bad. Negative 60 times 2 times 0.6. So I'm kind of working this piece. Oops, thought that was my purple one. This is negative 72 plus dB dt times 2 times 0.8, which is 1.6. And then 20 times 2 times 1 is 40. And now I'm just solving this like an equation. So I'm going to add the 72 to the other side. So I have dB dt times 1.6. Whoops, that's just to say 1.6. Equals 112. Okay. And then divide by 1.6, and I find out that dB dt is equal to 70. And then let's just think about what that 70 represents. That's the rate that this is changing. Now, all my other rates of change are miles per hour. So this is 70 miles per hour. So what we just found is that this distance is increasing at a rate of 70 miles per hour, meaning that that car must be moving at a speed of 70 miles per hour. Okay, we're going to move on to another example here. I do want to point out that this question I knew to use Pythagorean theorem because everything I was dealing with was lengths of sides. I didn't have any angles involved here at all. And I'm pointing that out because the next problem we are going to have an angle involved, a theta value. And when you have a theta value involved, that typically means you're doing some sort of trigonometry, SOHCAHTOA type stuff, okay? And so you will want to recognize the difference there, but here I didn't need to use SOHCAHTOA because I didn't have any angles or anything like that involved. Okay. And if that was overwhelming to you, I suggest you pause the video and maybe just read back through that example 2 or try it again on your own and then come back and watch example 3. But make sure you've got example 2 nailed down before you go on to example 3. Okay, picture. Hot air balloon is rising straight from a level field. So here's our field, okay? And here's my hot air balloon rising up into the air, okay? Being tracked by a rangefinder on the ground. So there's a rangefinder down here that is tracking how high up is that balloon. So once again, we've got a right triangle situation going on here, okay? Let's label some numbers. So the rangefinder is 500 feet from the liftoff point. So that's this distance down here. This is 500 feet. Okay. At the moment, the rangefinder's angle of elevation is pi over 4. So angle of elevation is down here on the ground, and this is pi over 4. Okay. The angle is increasing at a rate of 0.14 radians per minute. Okay, so we're dealing something with this angle. And we want to know how fast is the balloon rising. So we really are trying to figure out how fast is this changing over here. That's going to be a rate of change. There is some missing information here that I'll have to kind of dig for. But first, let's figure out what geometric formula or process is happening here. If we have an angle here, and then we have a side length and a side length, using SOHCAHTOA, that's a tangent situation, right? This is opposite and this is adjacent, okay? And so I'm going to set this up as tangent theta equals, okay, I'm going to do this. I'm going to say opposite over adjacent is really our formula here. When I did this in class, I labeled the opposite side with an O, and that made things very confusing because it made it look like a 0. So I'm going to use X to represent our opposite side, and I'm going to use A to represent our adjacent side, okay? Just so that doesn't get confusing later. So this pi over 4, this is our theta, okay? The opposite side is this side here, that's X, and then my adjacent side is this 500, so that's my A. Okay, and then the one other piece of information, this over here is a rate of change. It's increasing, so rate of change, 0.14 radians per minute. That's how fast this is changing. So we're going to label d theta dt as 0.14, and that's radians per minute, okay? And what we're trying to find here is dx dt. I want to know how fast is this changing. So dx dt is my question mark. That's the thing I'm trying to find. And I want you to think for a second about this 500. This 500 isn't changing, right? This is a constant. And so my dA dt is actually equal to 0, right? Because this number, this value is not changing. Those constants actually make these problems easier a lot of the times, okay? Because that 0 inside my derivative is going to wipe some things out. Okay, and then let's see. So the only other variable I'm missing, and in a second I want to make sure that I actually need this variable, but I don't have this value x, okay? I could find it using this formula, right? Going back in time to when we were just doing nice, simple SOHCAHTOA problems. But let's find our derivative first and make sure we actually need that x value. I mean, spoiler alert, we do, but let's pretend we didn't know that. So, okay, derivative. Derivative of tangent theta is secant squared theta. Oh, and then I forgot, that's times d theta dt. Didn't really forget, I just usually put it first and I put it second here. Okay. Oh, let's see. I'm going to short myself on space here. I might need to go down here a little ways. So I'm going to do my derivative down here. So secant squared theta times d theta dt. Now, to do my derivative over here on the right-hand side, technically that involves quotient rule. And there is a way, because this number is a constant, there is a way in this problem we could make that easier on ourselves. But because I know you're going to see some where you have to do quotient rule, I'm going to just stick with that. So thinking about this as x over a, okay? When I do quotient rule, I do derivative of the top times the bottom. So derivative of the top, derivative of x is just dx dt. And that's times the bottom, which is a, minus dA dt, derivative of the bottom, times the top, which is x. And then all of that is over my denominator squared. okay? Now, remember a second ago, we're going to fill a bunch of stuff in here. But remember a second ago when I said that 0 is going to make our life easier? This dA dt is just a big fat 0. So really this whole piece of the quotient formula crosses out. This goes away. Because when I put that 0 in, it's going to cancel everything out. And then also what's going to happen, and I'm doing all of this before I put variables in because I want to make sure I actually care about this stuff. The a and the a squared, I could cancel one of these a's with this a squared. So this a goes away, and then this guy goes away. Okay? So actually, if I cancel this out ahead of time, I don't need that x value. Okay? I don't need that length there. And so now I have secant squared theta, d theta dt, dx dt, and a. So let's just take inventory and make sure we have all of that. We know what theta is, right? We know what d theta dt is. dx dt is what we're trying to find. And then our a value is 500. So we can just put that there. Okay? So let's do that. So I have secant squared theta. So I'm going to do secant squared of pi over 4 times d theta dt is 0.14. And then this equals dx dt over a, which is 500. Okay? And then all I really have to do is multiply by the 500 over here on the other side. I do eventually want us to get to the point where we're not scared to tackle something like this by hand. Okay? Today is probably not that day. So for today, I'm just going to say we're going to multiply 500 by that secant squared. Let me show you how that's going to look in a calculator. So 500 times secant squared is going to be 1 divided by cosine of pi over 4, parenthesis, and then close the parenthesis again to close all this off. And then we need to square that. Okay, so that's my secant squared. And then times the 0.14. I just want to double check. I can't remember if I put the 500 in. Yes, I did. Okay. Oh, and then also, sorry, my calculator might not be, it is. I wanted to check and make sure I was in radians. And then let's hit that. And so we end up with 140 equals dx dt. And that 140 is a label. Let's see, this is talking about feet, and we're in minutes. So this is 140 feet per minute. Okay? Okay, so these triangle ones are going to pop up a lot. There's a lot that have to do with triangles. Again, I knew to use trigonometry here because I had to incorporate this angle somehow. So I wasn't using all of my side lengths. I wasn't using this hypotenuse at all, but I am using these two sides. Okay? And this was a case where when I went through and simplified this formula before I started, I didn't actually end up needing that x value. I could have found it using this tangent formula, but I didn't need to. Okay? So I'm going to leave that there. I think we're going to hit this example 3, or I guess it's the second example 3, in another video, because this gets into cones, and there is something funny that happens with cones. But let's make sure you can handle triangles. Okay, so tonight's assignment is mostly focused on triangles and trig versus Pythag and stuff like that. So give a few of these a try. Okay, have a great day.